My name is Neil. I'm a postdoc researcher in Weizmann Institute. And in the next 15 minutes or so, I will present my recent work on dynamic metasurface antennas for bit-constrained MIMO OFDM receivers. This is a joint work with Hanqing Wang and Jin She from Southeast University, with Reza Imani, Insang Yu, and David Mick from Duke, and with my superb supervisor, Yonina Elda. The focus here is massive MIMO systems, which is considered a key technology for next-generation wireless communications. To explain massive MIMO, we need to begin with conventional cellular networks, in which there is a multi-antenna base station serving a set of single antenna users. In the next generation cellular networks, we'll have a much larger number of users, which will also be diverse, not just cell phones, but other types of communicating devices. And one of the methods to handle the resulting increased demands is to equip the base station with a very large number of antennas. It was actually shown in the pioneering work by Thomas Zeta from 2010 that you can significantly improve the signal to interference and noise ratio when implementing a base station with a very large number of antennas. And that's, as a result, it's been the focus of substantial research attention over the last few years. However, implementing a base station with a very large number of antenna elements does not come without its challenges. One of those challenges is related to analog to digital converters, which allow electromagnetic waveforms propagating through the channel to be processed in digital form. The typical power consumption of each analog to digital converter is proportional to its sampling rate and its resolution. Now, if we look at massive MIMO system, we have a base station which is equipped with a very large number of antennas, which means that it has a very large number of analog to digital converters. Now, if we also want to operate with wideband signals, like in the millimeter wave regime, then essentially, in order to keep the cost reasonable and not to have to build a dedicated power plant for each base station, we would have to operate with low resolution ADCs. Another challenge is associated with the shape and size of building such large antenna arrays. And obviously, in the desert, we can hide our base stations inside cactuses. Not sure that will work in urban settings. Now, one of the emerging technologies for building antennas is based on dynamic metasurfaces. It allows to pack a very large number of radiating elements in a scalable manner. It operates in a relatively low power, and it has a dynamically configurable radiation pattern. Now, dynamic metasurface antennas have been applied over the recent years, mostly for microwave imaging and also for radar system. And in our recent work from 2019, we showed its potential when applying it to implement massive MIMO base stations. Now, the question we'll focus here in this talk is, can we use the model and the properties of dynamic metasurface antennas to facilitate the operation with low resolution analog to digital converters in massive MIMO communications? So to do that, I will begin with the model of dynamic metasurface antennas, understanding what they are. Then I will elaborate on task-based quantization, which is the framework upon which we design our dynamic metasurface antennas to operate with low resolution analog to digital converters. And then I will show the design and some numerical results. So we'll begin with metasurfaces, which is the basic building blocks here. And metasurfaces are essentially two-dimensional surface configuration of metamaterials. Metamaterials are artificial materials whose electromagnetic properties are externally controllable. Now, when you stack those metamaterial elements on top of a guiding structure, you get some sort of an antenna, a set of radiating elements. And the nice thing about it is that since you can now control the electromagnetic properties of each metamaterial element, you get a dynamic antenna in which you can control the radiation pattern. Now, if we look at what it looks like, those metasurfaces, each one of those elements here is a metamaterial element, and they lie on top of those one-dimensional waveguide, resulting in a large array of radiating elements called microstrip. So our metasurface antennas are essentially tiling of microstrips, each consisting of a multitude of radiating metamaterial elements. Now, as a result, what you can get is an externally controllable reflection or radiation pattern. Now, this has not been overlooked in the communication literature. Actually, over the recent years, there is a growing interest in using metasurfaces as passive reflectors, namely as means to extend and enhance wireless environments as some sort of intelligent relays. This has been the focus of a lot of works recently. Now, what we focus here is not on their usage as passive reflective surfaces, but on their usage as active massive MIMO antennas, namely not as relays, but as the actual base station. So this will be the focus of this work, not on passive reflective metasurfaces. Now, we need to understand the model of metasurfaces when used as dynamic antennas. We need to begin with the microstrip. So each microstrip is essentially a set of metamaterial elements embedded on top of a waveguide. So if those are the metamaterial elements we see here, and we have a received signal which is observed by each one of those elements, then it undergoes two main parts before it is recovered. The first thing is the frequency response of each one of those elements. Now, since we can externally control the electromagnetic properties of those elements, we can actually get a different form of frequency response for each element, which can look like a bandpass filter, can look like an all-pass filter. We can change its phase and its gain, but it's under the family of what's called Lorentzian functions. Now, after the signals go through the metasurface elements, they still have to propagate inside the waveguide before they are captured by the output port. Now, since the distance from the elements to the output ports is not identical, we get a different phase shift accumulated from each element. So in the end of the day, what we get from those microstrip is some sort of a hybrid analog digital receiver, because the signal which is observed by each element is captured at the receive port after going through the controllable frequency response of each of those elements, the propagation inside the waveguide, and then they're captured at the receive port. So we essentially have less RF chains than we have radiating elements. So that's actually a form of hybrid receiver, which are widely considered, widely studied in the massive MIMO literature as a way to reduce the number of RF chains. But this is not like conventional hybrid systems, which are based on phase shifters usually. Here we have a frequency selective analog combining, because we can actually tune a frequency selective frequency response for each one of those elements. It's also dynamically controllable, and it's an inherent to the antenna structure. Namely, we don't need to introduce external circuitry to get this hybrid property, this hybrid architecture. Now, to get a model, if we call Y the observed signal, Z the output of each microstrip, and we use Q and H to represent the frequency response of the elements and the propagation inside the waveguide, respectively, what we get is a model that looks something like this, where Q is a matrix which we can externally control. So now the question is, can we use this resulting model to facilitate recovery with low resolution ADCs? And the answer is yes, and to do that, we will turn to task-based quantization framework. Task-based quantization refers to scenarios in which you acquire a signal in order to recover some information embedded in it. For example, in communication, we acquire the electromagnetic waveform at the output of the channel, but we don't really care about this waveform. We are trying to recover, for example, a set of symbols which were transmitted. So when you have a task, you usually can tune your analog to digital converter to operate with low resolution while mitigating its distortion such that the task can still be recovered. Because you do not care about the analog signal, you care about the information which is embedded inside it. And actually, we have a series of works about task-based quantization, and the overall model which allows you to exploit the presence of a task consists of this hybrid structure in which you have this analog combiner here, which you tune it in light of the task, in light of the fact that you need to recover some information embedded in the signal and not the signal itself. And then you tune the overall system, both the analog combiner and the scalar quantizers and the digital processing, such that you can still recover the desired information accurately while operating with low resolution quantizers. So for the task of recovering a linear function of the inputs, we've actually derived exactly what the system has to be. Now, if we look at the analog combiner, well, the details are in the papers. This is from a very broad perspective. It consists of a two-stage processing. You recover the linear MMSE estimate, and then you do some sort of water filling, which throws away the weak eigenmodes, which are indistinguishable after quantization. Then you do some rotation, which minimizes the maximal variance and essentially allows you to operate with a relatively fine quantization without having to increase the number of bits and without overloading the dynamic range. So that's essentially the rationale. I again refer you to our paper, our TSP paper, for the exact details of how is it done. Now, if we go into our model, then for the DMA, we can actually look at the frequency response of the elements as a form of analog combiner. So the question is, can we design our analog combiner using results from task-based quantization? So if we look at the problem of OFDM signal recovery, we have a channel output which consists of the transmitted symbols going through the channel plus noise. And if our task is to recover the linear MMSE estimate, we want to design our antenna such that we can recover the linear MMSE estimate of the OFDM symbols S accurately, then it's exactly a task-based quantization problem. And we can use results from task-based quantization to tune the elements and just to incorporate the propagation of inside the waveguide into the channel, and we get this equivalent structure in which our receiver consists of the frequency response of the elements which we control externally. This looks like a task-based quantizer, and we take the propagation inside the waveguide and put it as part of the channel. Obviously, this does not come without its challenges, and the challenge comes from the fact that this matrix, you cannot be any matrix, right? It is dictated by the Lorentzian form. So it cannot be any matrix, while task-based quantization gives a specific form of this matrix, right? It has to include this water filling expression, this rotation. You cannot do any, you cannot implement it using this kind of constrained matrices. So we proposed an algorithm to do that. Our algorithm simply operates in a two-stage manner. It first sequentially tunes each microstrip in light of task-based quantization results, and then it projects it into the feasible set, which is dictated by the frequency response of the elements. I will refer you to our paper for the actual details of how this algorithm is carried out, but looking into numerical results, we can see that it works pretty well. So if we see here, if we look here, the black curve is the linear MMSE estimate versus the number of bits. It obviously does not depend on the number of bits because it's unquized version. And the purple curve is the tuning of phase shifters, which was presented in this paper by Roth et al., which also looked at hybrid receivers with phase shifters. And what we see here, the green curve and the blue curve are the performance, the MSE achievable using DMAs tuned by our proposed algorithm, where the green curve looks only on frequency flat elements, and while the blue curve actually exploits the ability to get frequency selectivity of these elements. And as we can see, we get notable performance gains, not that far from what would have happened had we had no structure constraint on the microstrips. Furthermore, these results are also translated when we look versus SNR. So as we can see, the performance scales with respect to SNR similarly to the linear MMSE receiver, which operates without quantization constraints, and similarly to having any microstrip one could have had, which is essentially the task-based quantization results, and much better than previous results which use just phase shifters. And this also comes without the requirement of adding additional external circuitry to implement this analog combining, because it's an inherent byproduct of the antenna architecture. So in this talk, I've presented dynamic metasurfaces, which is an emerging radiation technology of scalable, low-power, planar antennas. And we showed its model, which ends up being some sort of a hybrid beamforming receiver with tunable frequency selective analog combining. And it does not require dedicated combining circuitry, namely it's all an inherent byproduct of the antenna architecture. We show that it can be exploited to facilitate operation under bit constraints by considering task-based quantization methods. And we showed performance gains over conventional hybrid receivers. Now, most of the details can be found in our archive paper available in this link. I want to thank you all for joining me for this call, for this talk, and wish you all to enjoy the rest of the conference. So thank you very much.